we'll be using the Millennium Falcon being chased by a Star Destroyer to illustrate the physics principles involved in describing inertial frames of reference. An inertial frame of reference in the Star Wars universe is a reference frame that moves at a constant velocity through space. According to Galactic Physics 101, akin to Newton's laws in our world, in an inertial frame of reference is an object that will remain in its state of motion, either at rest or moving uniformly unless influenced by an external force, such as a tractor beam or a hyperdrive engine. Imagine we have two frames of reference in a standard setup, the unprimed frame, F, which we'll associate with the Millennium Falcon, and the primed frame, F', which represents a Star Destroyer moving at velocity v relative to the Falcon along the x-axis. In the context of pre-relativity physics within the Star Wars galaxy, time flows uniformly for all observers, regardless of their relative motion through space. This principle allows us to apply straightforward transformations between these frames, akin to how Han Solo might calculate his flight trajectory relative to the Star Destroyer, considering both ships moving at constant velocities and the consistent passage of time across the galaxy. We can relate both of these frames of reference using the Galilean Transformations. Alright, let's geek out science fiction fans. Let's dive into Galilean Transformations with a little help from a galaxy far, far away. Imagine we have two inertial reference frames, the Millennium Falcon's reference frame, F, and a Star Destroyer's reference frame, F'. They're zipping through space with the Falcon moving at a constant velocity v relative to the Star Destroyer along the x-axis. The Star Destroyer is trying to capture the Millennium Falcon with its tractor beam. The guidance computer needs to be able to target the Falcon. What are the equations needed to be able to program the computer? In this scenario, we're going to use the Galilean Transformations to figure out how measurements in these frames relate to each other. Remember, in classical physics, time ticks uniformly everywhere, and spatial axes remain unchanged between observers. We'll assume that the Millennium Falcon and Star Destroyer are moving in the same direction at a constant velocity. So, here are our equations. 1. The time coordinate axis in the Millennium Falcon's frame, TT, is exactly the same as in the Star Destroyer's frame, T'. We can relate these two different time measurements by the equation T equals T'. 2. The x-coordinate axis in the Falcon's frame is labeled X, where x' is the coordinate in the Star Destroyer's frame plus the product of the velocity v and the time T'. 3. The y-coordinate axis, both frames remain identical, where y is the coordinate for the Millennium Falcon and a y' is the coordinate for the Star Destroyer. 4. The z-coordinate axis. Similarly, the z-coordinate axis is the same in both the Falcon's frame Z and the Star Destroyer's frame Z'. Think of it like Han Solo navigating the Falcon past a massive Star Destroyer. What Han measures in terms of time and position relative to his ship should match what Darth Vader calculates aboard the Star Destroyer, assuming they're both using these Galilean transformations and neither ship is maneuvering dramatically. The technician on board the Star Destroyer can use these equations to program the targeting computer for the tractor beam. Remember, these equations help us understand how physical events, like the Falcon dodging turbo laser fire or Vader deploying TIE fighters, will appear differently depending on your point of view, just like different observers in relative motion in our universe. The space-time interval measures the separation between two events in both space and time, akin to a generalized Pythagorean theorem. It gives us the distance that is invariant or doesn't change that both observers can agree on. In the case where the Millennium Falcon is being chased by a Star Destroyer, the interval gives the absolute or true distance between both spacecraft. Recall that the Pythagorean theorem in Cartesian coordinates gives the distance d between 2 points. By the formula, d equals square root of x1 minus x2 squared plus ida1 minus y2 squared plus ze1 minus y2 squared. The spacetime interval extends this concept to special relativity, where we must consider distances in both time and space together. Consider an event E1 happening at coordinates ct, x1, y1, z1, and a second event E2 at ct, x2, y2, z2, where c is the constant speed of light. The spacetime interval, denoted as ds squared, is defined by d squared equal to the minus c squared times, multiplied by the time difference squared, plus the difference in distance along x squared, plus the difference in distance along y squared, plus the difference in distance along z squared. Or more succinctly by the equation, an interval can be categorized as time-like, space-like, or null, depending on its relationship to the speed of light. If d squared is less than 0, it is time-like. If d squared is equal to 0, it is null. If d squared is greater than 0, it is space-like. We'll talk more about this in a later video. When the distance between two events is infinitesimally small, then the interval simplifies to the equation where the d represents an infinitesimally small distance. We also define proper time. This refers to the time interval experienced by an observer who is in motion relative to another given reference frame. Whereas the coordinate time can vary depending on the observer's state of motion, proper time is invariant. It remains the same regardless of the observer's velocity or position. From the interval equation, we can calculate the proper time. The proper time dTi is defined as: in special and general relativity, the spacetime interval ds between two events is a fundamental quantity. It is important because it remains unchanged regardless of the observer's state of motion. This invariance is profound because it means 1. Universal consistency. Different observers, regardless of their velocities relative to each other, will all measure the same interval ds between the same pair of events. This ensures a universal standard for how spacetime is perceived across different inertial frames. 2. Physical meaning. While measurements of space and time intervals, like distances and durations, may vary depending on an observer's velocity, the interval ds encapsulates a combined measurement of both space and time that all observers agree upon. It provides a consistent measure of the separation between events in spacetime. 3. Foundations of relativity. The invariance of the interval underpins key phenomena in relativity, such as the constancy of the speed of light and the relativity of simultaneity. It supports the framework where space and time are intertwined, and their measurements depend on an observer's relative motion. 4. Practical applications. In practical terms, this invariance allows scientists and engineers to make accurate predictions and calculations that are independent of the observer's frame of reference. It enables the formulation of laws of physics that hold universally across all inertial frames. In summary, the interval's invariance signifies a fundamental aspect of relativity. Despite differences in how observers perceive space and time individually, they all converge on the same understanding of the space-time interval between events. This universal consistency is a cornerstone of Einstein's theory, shaping our understanding of the cosmos on both large and small scales. If you enjoyed this video, please click the like button, post a comment, and subscribe to my channel.